This is slide 9 of the NMR PowerPoint labeled Chapter 14, Section 1 through Section 3. And there is some question about how the different signals, and of course we call them signals in NMR, not necessarily peaks, and you'll see why that is in a moment. The position of these signals changes with the unique chemical environment that these protons find themselves in. So, first off, we use an external magnetic field. So B0 is the external magnetic field. And this is what lines up all the protons, or the nuclei of the protons. They're all spinning in the same way. And they can either be spinning with the magnetic field, so that would be a lower energy level, or they could absorb energy, h nu, and actually this is a radio frequency, so you'll see RF sometimes, a radio frequency electromagnetic pulse that flips this from aligned with the external magnetic field to going against it. So this corresponds to going one way, this corresponds to the nuclei spinning the opposite direction. Okay. The difference in these two spin states, either with or against, is directly related to the magnetic field that the nucleus feels based upon this external magnetic field. But there are things that can affect the magnitude of this external magnetic field, and that's the unique environment that these protons or proton nuclei find themselves in. So here it says a proton is surrounded by electron density, right? So that electron density essentially opposes this external magnetic field and reduces it somewhat. So if there's more electrons around, it has a greater shielding effect on this external magnetic field. So this nuclei here is going to feel less of a external magnetic field because of this opposing magnetic field, and that makes this distance smaller. So whoops, it's going the wrong way, so it should be against the magnetic field, right? So it makes the two spin states closer together. This is shielded, this would be unshielded. So a larger induced magnetic field, this opposes the external magnetic field, and the nuclei feels a smaller resultant field, so we get, again, these two spin states that are closer together. Increases the electron density around the nucleus, so we have more electrons. So what can I say? This is the case where we have electron density increases around the proton. Now the thing about this is you don't really increase the electron density so much. There is a case where you do, and these are electron donating groups. Electron donating groups. You may recall way back, I think it was chapter 2, where we talked about the difference in the strength of acids and bases. We had electron withdrawing groups and electron donating groups. Alkyl groups are electron donating groups. So we could have a methyl group, or maybe we could have, well, you'll see this in the next chart, in fact. We could have maybe 3 methyl groups. These are electron donating. They're donating electrons through these sigma bonds to this carbon, and that deshields this proton. So it shifts the signal upfield to a smaller, we use again parts per million, or if you wish, a smaller radio frequency, so less energy. The opposite of this is when it's deshielded. Okay. So this is electron withdrawing. If you're withdrawing electrons, let's go back here a moment. Remember, it's these electrons that oppose the magnetic field. If you withdraw these electrons, there's less of an opposing magnetic field from that electron, and the protons feel more of the external magnetic field. So electron withdrawing groups, such as heteroatoms, essentially. Heteroatoms. So oxygen, nitrogen, halogens. So you notice here the opposing magnetic field here is larger. That makes this, essentially we can kind of lop off this much of the external magnetic field, so it's a smaller magnetic field. Here, the electron withdrawing effect reduces this opposing, so we have a smaller decrease, if you wish, and then the nuclei feel a larger external magnetic field, and this, well, I'm going to put this here. So this means that the two spin states are farther apart. We have a larger radio frequency that is required to flip that nuclei. This means the signal shifts downfield to larger ppm, larger energy, a larger radio frequency corresponding to the difference in these two spin states. So again, some vocabulary here. Upfield is shielded. Downfield is de-shielded. De-shielded, downfield. Right, de-shielded. And here you see the de-shielding effect of this electron withdrawing chlorine. Okay, so here we see the electron withdrawing effects of these heteroatoms, these nitrogen, oxygen, or halogens, and it shifts them downfield. Okay. We also talked about the effect of pi electrons shifting these guys downfield. So the pi electrons of an sp2 shifts them downfield, but for, this is sp hybridized now, this has two pi sets of electrons. So let me draw it here. We have a sigma bond here, and then we have the pi bond on the top, that's electron withdrawing, and then a pi bond in the front and back. And if we look at the orbital diagram of acetylene, and because these two pi clouds are 90 degrees apart, one of them cancels the other, and so it actually shifts it upfield. So it's not an additive effect, it actually cancels out those pi electrons, and so you see a kind of a strange effect here, going from sp hybridized to downfield sp2 and then back upfield a bit to sp. So know this, right? It'll make life a lot easier if you just kind of memorize this. We have benzylic, these are referred to as benzylic hydrogens or protons, right? Those that are directly attached to the ring. Some of the most highly de-shielded ones are those that are adjacent to a carbonyl, because it's not only is it polar, but you also have the pi, where is it? The pi clouds of sp2 hybridized carbon. Same thing here, even more highly de-shielded, because you have the hydrogen directly attached to an oxygen. For alcohols and amines, they're actually, there's a broad range here, but I don't know why they're on the bottom here. There should be actually be, maybe because it is such a broad range, but we'll talk more about these guys later. Okay, this is where we had left off before COVID caused all that chaos. So I'll stop the video now, and we'll pick this up in the next lecture.